Okay, this week in lab, we're going to be doing a dioxic growth curve experiment and also combining that with a viable count. So we're going to be determining the viable number of bacteria in a broth culture. So combining two different principles. So there's a handout that's on the Blackboard site that you should definitely make yourself familiar with before lab, but also just to help you prepare for this. When you come in, each of your lab groups is going to have a time point assigned to them. And at your assigned time point, you're going to take a sample from an E. coli culture growing in a minimal defined media. So it looks very much like water. So I just inoculated this media a few minutes ago, so I'm going to take the ×0 time point. And so I'm taking a 500 microliter, or 1/2 of 1 mil, aliquot. These are in magnetic clamps, so you can just set it back into there, close the cover, and it will begin to grow. Okay, now with that 500 microliters, the first thing that we're going to do is to take an optical density reading. So we're going to use a spectrophotometer to determine how much light is absorbed by this particular culture. So there are cuvettes here that you will pipette your 500 microliter sample into. You're next going to use, so this is my sample. This is the spectrophotometer. It's set to 600 nanometers wavelength, so it's passing a light beam through a chamber at 600 nanometers. I have a blank, so this is a cuvette that has the sterile media that the E. coli is growing in, but no E. coli have been put in here. So we're first going to blank the machine so that if there is any innate absorbance to that M9 minimal media, we can tell the machine that it's 0. So I put that blank in there, and I'm going to hit this button that says 0 absorbance, and it's going to set the machine to 0. You'll do this before you put in your sample. As soon as you get a reading that says at 600 nanometers you have a 0.000 absorbance, A stands for absorbance, you know the machine is blanked. So you can now take that blank out and insert your culture. Close that up. You don't have to hit anything else. It will automatically read the absorbance. This is my ×0, so I didn't expect very much absorbance, and I don't have very much absorbance, 0.002. So the principle here is that the more bacteria there are in that broth, the less light will pass through. More light will be absorbed. So the bacteria absorb the light, they scatter the light, and as these numbers, these absorbance numbers get higher, that's an indication that the bacterial culture is more dense. It has more bacteria per mil. So that's one way to determine how many bacteria there are per milliliter in a culture. You're actually going to establish an equivalency. You're going to calculate how many bacteria per mil it is for each one of these absorbances. So in the next portion of this is at this point you're not counting viable cells, you're counting total bacterial cells. In that cuvette, a dead bacterium will absorb or diffract light to the same degree that a living bacterium will. So this is in essence looking at total number of bacteria. In this particular case, since the culture was just inoculated, we can pretty much assume that all of the bacteria in there are alive. But now we're going to do a viable count. So the first thing that you're going to do with this is I'm going to take out the cuvette containing the culture, the 500 microliters of culture that I just used in the spectrophotometer. And I'm going to set up a serial 10-fold dilution. So what I've done is I've taken 7 sterile glass tubes, and I've labeled them 10 to the minus 1 through 10 to the minus 7, reflecting the dilution series that I'm going to do here. So the next thing that I'm going to do is to set the pipettement to 9/10 of a mil, 900 microliters. So 0 in red, and then 90 is 0.9 mils, or 900 microliters. And now I also have out autoclaved sterile, so it's sterile distilled water. I'm now going to transfer 900 microliters into each one of these tubes. As I do that, there's a tendency for you to want to just stick the pipette tip in here and shoot that shoot that water out. Instead, what you want to do is to put the pipette tip as close to the bottom as possible and expel it, because you don't want water splashed up in spots on the side, because it's important that there's precisely 900 microliters in the bottom of each one of these tubes. So that's 10 to the minus 3, 4. I realize this is a bit like watching paint dry. I lost a drop there. Probably in other lab classes you've learned the principle of serial dilution, but it never hurts to review. Now, with the caveat that this is not the best sterile technique that you're ever going to see, I'm going to use the culture that I put into this cuvette as my starting solution to do these dilutions. The cuvettes themselves were not sterile, but as you think about this, I want you to ask yourself the question is like, why is Mark really not very concerned about the fact that he's potentially introducing bacteria other than E. coli into this dilution series? So what I'm going to do is I've now set the pipettement to 1/10 of 1 mil, or 100 microliters. So I'm going to go down again, first stop, I'm going into that cuvette, I'm pulling up now 100 microliters, and I'm going to put that 100 microliters into this first tube. And then I'm going to triturate or pipette back and forth to rinse the bacteria out of that. I go down to the second stop to make sure I've gotten rid of the last drop. I pull that out, and now very importantly, I get rid of that pipette tip. It's very important that you change pipette tips between every one of these dilutions. This is your 10 to the minus 1 or 1 to 10 dilution. Think about, visualize what you're doing. If, let's say for instance, there were 10 million bacteria per milliliter in that starting culture, and there are not, but if there were 10 to the million bacteria per mil in the starting culture, there are now 1 million per mil in this tube. It's a 1 to 10 or 10 to the minus 1 dilution. I've gotten rid of that pipette tip. Now, my way to make sure I don't confuse myself is I'm setting that back into a different row, because now I want to put on a new pipette tip. I'm going to take 100 microliters from that 10 to the minus 1, and I'm going to put that into the 10 to the minus 2, and I'm going to pipette back and forth or triturate to rinse that pipette, push out to the second stop to make sure I've left it all behind, change the pipette tip. That's my 1 to 100 dilution, or 10 to the minus 2. So if there were 10 to the million bacteria in the original culture, there were 1 million per mil in the 10 to the minus 1. There are now 100,000 per mil in this culture. So now I'm going in with a new pipette. I'm going to pull out 100 microliters of my 10 to the minus 2, set that aside, put it into 10 to the minus 3. As you do something as repetitive as tenfold dilutions, it's difficult not to get distracted, not to do things like I'm doing and carry on conversation, because it's very easy to forget where you're at, where you are, what you've pipetted into, what you've pipetted out of. Did you change the pipette tip? There's lots of ways that you can make an error as you're doing this. So it's important to stay focused. Even as I'm talking to you right now, I'm beginning to think, have I made a mistake? Did I forget to change pipette tips? So I'm just going to do the rest of this in sweet, blessed silence. And then once I go into the last one, just for good measure, I'm going to take out 100 microliters and discard it. That's just to make sure that all of these tubes have the same volume in them. They all have now 900 microliters of various dilutions. It's really not critical for the type of counting that we're doing now that I took that last 100 microliters out. If we were counting the total number of bacteria in these mills, then that last extraction would have been important. But in this particular case, it isn't. But just for good practice, throw away 100 microliters from that. So now, I'm going to set these aside for just a minute. I've gone ahead and pre-labeled, as you will do, 7 different plates. These are trypticase soy agar plates. So these are rich media. I've labeled them as ×0, the dilution, today's date, and my initials. So you can almost never put too much information on a plate, but it's very easy to put too little information on a plate. And again, just as a reminder, always label the agar side and not the cover side, because as these get stacked in the incubator, if the stack is knocked over, there's no guarantee that the right cover gets back on the right plate. But if your labeling is here, you're in good shape. Now, in order to, what we're going to do is add some of these various dilutions to these various plates and distribute them. In our lab, the way we distribute those plates is actually kind of fun and almost musical. You're going to turn all of your plates, once they're labeled, upside down, and you're going to take these world's smallest marbles. These are 5mm glass beads. They're autoclaved. You can tell by the time tape that they've been autoclaved. So they are sterile. And I'm going to sprinkle carefully 8 to 10 of these little marbles onto each plate. Most times, if you've never done this before, you'll bounce some onto the bench top and they'll roll around, and that's fine. Part of the reason why I have you put the, see, right on cue. Part of the reason why I have you put the beads on first before you put the bacteria on is if you had already put bacteria on these plates and some of these little beads bounced off and started rolling around, you could be carrying the bacteria, the E. coli, around on the bench. I'm going to cap this back up. Now, there's a temptation to want to pick these up and put them back in there. They're not sterile any longer. So we're going to recycle these. We're going to use them again. So I'm just going to set them aside and hope they don't roll too far away. Now, once I've got the beads on here, now we're going to go to these carefully prepared dilutions. And we're going to put onto each one of these plates 100 microliters. So the same volume. Now, I'm going to show you a little trick that's going to help us be a little bit more green, a little bit more sustainable. I mentioned that when you were doing the dilutions, you had to change pipette tips every time, because you were going from a high concentration of bacteria to a low concentration of bacteria. What I'm going to do is I'm going to now start from the most dilute, the 10⁻⁷ I'm going to take 100 microliters from that very dilute. Perhaps there's not even any bacteria in there. And I'm going to plate that onto the 10 to the minus 7th plate that already has the beads. I don't need to change pipettes now because this had so few bacteria and this has 10 times more, that if I go into this 10 to the minus 6 tube, I can use the same pipette. I'm just going to mix them up a little bit. Put that on. We go to 10 to the minus 5. Pull out 100 microliters. Minus 4. Minus 3. That's the 1 to 1,000 dilution. 1 to 100 dilution. And 10 to the minus 1 dilution. Get rid of that pipette tip. Now comes the fun, almost musical portion of our program. I'm just going to stack these up. Perhaps we can turn some music on in the lab, because now what you want to do is to use those beads to distribute that bacterial culture evenly across the plate. So having 7 plates to do this with about 10 beads per plate gives you a nice percussion. Now, don't, when you're doing this, do a circular motion, because then all of the beads go to the outside and all of your bacteria are distributed just around the center. So you want to go back and forth, forward, side to side, minimal amount of circular motion. Do that for 15 or 20 seconds until you're pretty sure that you've got those bacteria randomly distributed across that plate. Now, we're going to, so these are those little beads that escaped me. I'm going to put them in here because this is where I'm going to add all of these contaminated beads. We're going to put alcohol in. You'll actually be dumping yours into an alcohol vat to disinfect beads that will eventually get cleaned and autoclaved, thanks to the hard work of your TAs. Okay, so that is a completed dilution series. Those will go in the incubator to go overnight. Now, like every good cooking show, I went ahead and yesterday I titered out a culture and I diluted it out to 10 to the minus 8. So these are E. coli plates, same type of plates, tryptase soy agar plate. Here's well, let me first show you what the uninoculated plate looks like. You know what those look like. At 10 to the minus 1, it's practically a lawn. Many too many colonies to count. As a matter of fact, the colonies are touching one another. Here's the 1 to 100 dilution of the culture that I did yesterday, and again, the colonies are touching one another, too numerous to count, TNTC. At the 1 to 1,000 dilution, you can see that there are less colonies, but there's still way too many to count. Once we get out to 10 to the minus 4, now you can see individual colonies, but still, I wouldn't even make the TAs count that number of bacteria. 10 to the minus 5, now we're getting someplace. Here, you could reasonably count the bacteria on that plate, and probably should. What you would do to make counting easy, because you will be doing this counting, to make sure that you don't count the same colony twice, you're going to take a Sharpie, and as you count them, you're going to go 1, 2, 3, 4, 5, 6, 7, 8, and count an entire plate. Now, you want to look for a plate that has probably no more than 250 colonies, because if there's more than 250, there's a chance that you'll miscount. And you want to have a plate that has no less than 25, pipetting error could really skew your results. Here's the 1 to 1 million dilution. So this would definitely be much more countable. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've already bored you enough. I'm not going to make you count with me or watch me count this, but this would be a nice countable plate. This is hopefully what you're going to find somewhere in your dilution series. And in the handout, we'll talk about how it is that you'll do the calculation. So you can calculate the titer of your culture at that particular time point, either by using a formula or simply by logically reasoning it out. So that's better described on your handout, and we'll also be talking about that in lab one-on-one. If you continue on, here's the 10 to the minus 7. There are actually 3 colonies on here. I wouldn't use this to determine what the titer was, because, you know, if this were off by even 1 colony, that would be a 25 or 33% change in the results. So I wouldn't be able to trust that result as much as if I were counting 25 or 30 or 50 colonies, because then a minor pipetting error wouldn't have a major effect on my calculations. And then of course, at 10 to the minus 8, the plate has no colonies. So we've eventually diluted out beyond where the culture is. For your time points, you're only going to go as far as 10 to the minus 7. This was an overnight culture that had grown to high density. So I suspect that in this minimal media with glucose or glucose and lactose, that the bacterial numbers are not going to reach quite this high a number. So I suspect that 10 to the minus 7 dilution will be sufficient. Okay, I hope that helps clear things up in your mind as to what we're going to do in the lab. We'll talk more about the actual mechanism, as we have in lecture, of dioxy and viable cell counts. But hopefully this helps, and I'll see you in lab.